this lesson. So in this lesson, we're going to continue our discussion of what we started in the last lesson. So in the last lesson, we used Taylor's series to approximate a first derivative, and we came up with three techniques: the forward, backward, and centered finite difference, right? And we described what the forward finite difference is. It's basically taking the point that we're interested in getting the derivative at and taking a point forward to it. And the derivative between those 2 points is going to be the approximation to the true derivative that I'm interested in here. And the backward is taking the point that I'm interested in and taking a point backwards to it, and the derivative between those 2 points will be my approximation. In the centered, we take a point forward and a point backwards, and the derivative between those 2 points will be my approximation. Now in this lesson, we're going to learn how to code those functions, the forward, centered, and backward in VBA. We're going to be applying this on the function ln of x plus x squared, and the point that we're interested in getting the derivative at is x equal 1. What we're going to do is we're first going to get what the derivative is analytically, the exact derivative, and then we're going to approximate it using the forward, backward, and centered, and we're of course going to compare it with the analytical through calculating the error. Also, in the last lesson, I explained that the accuracy of these techniques is dependent or very sensitive to the step size. So if we reduce the step size, the approximation becomes more accurate, and we're going to see this in this lesson quantitatively. So the first thing I want to do is I actually want to code the function, and this is something I want to explain. If there's a function that you're using more often in your code, it's best that you define it initially, then call it. That's going to save a lot of time in terms of writing it over and over again. So if I say function f, and my input is going to be x, I'm going to say f is equal to log of x, and we explained that log in VBA is the natural log, and it's going to be plus x power 2. So now I defined my function. So later in my code, I can just call f, and it's just going to call this function. The first thing I want to do is I want to calculate the derivative at x equal 1 analytically. Now, using the differentiation rules, as you remember, ln of x, the derivative of it is 1 divided by x, and x squared using the power rule is 2x. So I can create a derivative function here, and I can call it dy dx, and my input is going to be x. And I'm going to say dy dx is equal to 1 divided by x plus x, or plus 2 multiplied by x. Now at x equal 1, you can see that 1 divided by 1, that's 1, plus 2 multiplied by 1, so I should get the derivative at x equal 1 to be equal to 3. So if I come here and call this function that I just coded, dy dx, and I evaluate it at 1, if this was coded correctly, I should get 3. Now, given that I now have coded the function and I coded its derivative, now let's actually code the forward finite difference and compare it to the analytical. Now, the one thing before I code the forward finite difference is I want to explain what is meant by xi plus 1. Now, plus 1 doesn't necessarily mean I'm going 1 unit forward. It means that xi plus 1 is xi plus the step size that I choose. And the step size is basically the distance between those 2 points. For example, if my xi, the point I'm interested in for this example, is x equal 1, and I choose a step size to be 0.5, that means xi plus 1 is xi plus 0.5, which is going to be 1.5. And for that reason, when you look at this equation is really defined in 2 things, right? It's defined in the xi, the point I'm interested in getting the derivative at, and also the step size that I choose. So if I do function, and I'm going to do ffd, forward finite difference, I'm going to need xi, the point I'm interested in, and I'm also need the h. I'm going to say forward finite difference is equal to, and this is why I said it's very important, or not very efficient, if I code this here, instead of writing log of x plus x squared, I can just call f. And what I want to do, I want to evaluate it at xi plus h, because we said that xi plus 1 is xi plus h, minus f of xi. and I'm going to divide this by h. And this is coding the forward finite difference. Now we have an equation for the forward finite difference. So if I come here and I say forward finite difference, now for it has two inputs. The point I'm interested in, which is 1, and I'm going to get it at a step size of 0.5. So if I do a step size of 0.5, I have 3.31. Okay, so my analytical is 3. This approximated at 3.31. So let's actually get the error for that. So I'm going to say the absolute. I'm going to open two parentheses, and I'm going to say the true value minus the approximate value divided by the true value. So I have 10.36% error. Okay, so let's see the effect if I actually use 0.25 as my step size. So if I say forward finite difference, the point I'm interested in is 1 and 0.25, would that change? I'm at 3.14. So I'm actually closer to 3. So you can see as I reduce the step size, I'm actually getting a more accurate answer. So there's one thing I want to do in terms of Excel here. I want to keep this true value constant. And what I do is I can actually just press F4 and here F4. And the reason I'm doing that is because I'm going to drag this here. And when I drag this here, you can see that it kept this constant, these two values constant, but it moved to this one. And you can see that I have 4.75% error as compared to 10.36% when I went from 0.5 to 0.25. So I halved the step size. So what about if I halve the step size even more? So if I drag this, it's going to be the same number, but let's go in here and change it to 1, 2. And we can see that I went to 3.06, so I'm getting closer and closer to 3. So if I do autofill here, I am at 2.15%. So you can see, as I'm reducing the step size, how more accurate my approximation becomes. So given that we're done with the forward, let's actually go to the backward. And just for ease, let's copy this, because they're very similar codes. And let's change this to backward finite difference, and this to backward finite difference. And here, the difference is, the first one is xi, f of xi. And the second one is f of xi minus 1. And we said it's very similar to f of xi plus 1. It's just this is going to be xi minus h. And we're done with coding the backward finite difference. So if I came here and I said backward finite difference, and the point I'm interested in is in 1, and the step size I want to use is 0.5, and you can see I'm at 0.88, so it's approximating it from the other side, which is not surprising. And if I drag this here, it's going to give you the same number, but I can go in here and change this to a step size of 0.25, and we can see I'm getting closer to 3, so by reducing the step size as well, I'm getting a more accurate answer. And I would do 1.12, and I'm getting closer and closer to 3. So let's actually drag this down, and you can see here, by locking these two, it's just changing where I'm getting my approximation from. So here we have 3.79%, so we can see if in this case, the backward was more accurate than the forward. And this is the thing, with the backward and the forward, it's dependent on the function. Sometimes the forward is superior to the backward, and sometimes the backward is superior to the forward. So let's drag this and see what's going to happen with the error in terms of these two. So it went from 3.79 to 3.31% to 1.82%. So again, you see with the backward as well, as I'm reducing the step size, I'm getting more and more accurate answers. And for this particular function, the backward seems to be yielding more accurate answers than what the forward would. So let's actually copy this and create the last one, which is the centered finite difference. And the centered finite difference, as you can see here, is xi plus 1, so it's xi plus h, and minus f of xi minus h, or here is minus 1, and it's divided by 2 times h. 2 multiplied by h, and I forgot here a parenthesis, and those two have to match. So center finite difference here, and the function is center finite difference equal to that. So let's actually call it down here, centered finite difference, and the point I'm interested in getting the derivative is 1, and my step size is 0.5, and I have 3.09, and if I drag it here, it's going to give the same answer, but let's go in here and change it to 0.25, and change this to 1, 2. So you can see we started at 3.09, and then it went to 3.02 to 3.0048. So let's see what the error is going to be like. So you can see we started at 3.29, and it reduced to 0.72, and it reduced to an error of 0.16% when I used the step size of 0.12. But you can see here that the one that is superior to all of them is the centered finite difference, and we explained that visually, as you can see from this one compared to these two, and also because this also from the truncation error is h to the power 2, and we explained that in the last lesson, that the center finite difference is superior to the forward and backward, and we can now see it quantitatively down here. Now in terms of, again, the forward and backward, it depends on context, it depends on the function that you're dealing with. Sometimes the forward is more superior than the backward, and sometimes the backward is more superior than the forward. So what did we learn in this lesson? So in this lesson we reviewed what is forward, backward, and centered finite difference. We learned how to code them into VBA. We also learned how each one of those techniques are sensitive to the step size that you use. And the lower the step size that you use, the more accurate your approximation becomes. But despite that, we see that the centered is more superior to all the forward and backward techniques. Well, this marks the end of this lesson, and I'll see you in the next lesson.